Hey guys, 9.3, rational functions and their graphs. So today we are looking at how to identify some of the properties of the rational functions, and then we're also going to graph a rational function. All right, let's take a look at this first slide. A rational function. A rational function is any function that can be written as a fraction. And more specifically, for it to be rational, or with respect to this section, the denominator should be some sort of algebraic expression. Take a look at these examples. So this one is negative 2x over x squared plus 1, 1 over x squared minus 4, and then x plus 2 times x minus 1 all over x plus 1. You can read through the rest of this if you want. There is a point of discontinuity when your denominator equals 0. So let's go ahead and take a look at that. So finding the points of discontinuity is when you find the values of x that make the denominator equal to 0. Looking at example A, we look at just the denominator. So we have x squared minus x minus 12 equals 0. Find factors of negative 12 that will give you a negative 1. So we are going to do negative 4 and positive 3. We have x minus 4 times x plus 3 equals 0. Now, in order to solve each of these x's for 0, we set each expression equal to 0 and solve for x. So x is 4, x is negative 3. We have a point of discontinuity at 4 and at negative 3. Okay, now looking at B, we're going to look at this denominator. So we have 3x squared plus 4 equals 0. Subtract 4 from both sides, and now you have 3x squared equals negative 4. Divide both sides by 3, and now you have x squared is negative 4/3. In order to solve this for x, we need to take the square root of both sides. And right about now is when you're going, we can't do that, right? Stop. Because this is negative. If it wasn't negative, we could do it. But because that's negative, there is no real answer. So this one has no points of discontinuity. Okay? And I was asked lots of questions about the numerator. It doesn't have any effect on or have anything to do with the points of discontinuity. It does have something to do with the future, but just not yet. All right. Next example we have. Oh, we want to talk about this first. This is either the difference between vertical asymptote and the holes. So if you take a look at this graph over here, you can see that we have two places where the function does not exist. And you can see these are vertical asymptotes. Well, we find those vertical asymptotes by finding where the denominator equals 0. So point of discontinuity, because it's not a continuous function. So x is 1 and x is negative 2. And now you see an example of that graph. Okay, and it only has vertical asymptotes. The second graph we have, we notice that we have a algebraic expression that is the same in the numerator and the denominator, and you can see that in this statement here. If you have an expression that is the same in both the numerator and denominator, then that is known as a whole, not a vertical asymptote, but a whole. And you notice there's nothing else left in the denominator once you've identified these as a whole. So there's nothing else except for this hole. And that's what it looks like. It does look like a gap in the equation, in the graph. All right. This one, excuse me. Okay, so looking at this one, we have the graph of this function. Y is x minus 2 over x minus 2, x minus 1. Alrighty. So we've got this. So we know we have a hole, and that hole is at x is 2. We also have this x minus 1 still hanging out there. Nothing's going on with that. And because of that, we know that we have a vertical asymptote at 1. And so you can see that right here. So we have a vertical asymptote and a hole. Cool beans. All right, let's go ahead and get started on the next example. All right. Describe the vertical asymptote and the hole for the graph of each rational function. All right, looking at A, is there x minus 7 in the denominator? No. So I know that I have, could have done it the other way, no holes. As far as asymptotes go, I have 2 points of discontinuity in the denominator. So for a vertical asymptote, we have when x is negative 1, because it has to be the opposite, and x is negative 5. Over here, notice that we have x plus 3 in both the numerator and the denominator. So that is a hole. And then your vertical asymptote, there's nothing left in the denominator. So in this case, there is none. Finally, looking at this beast, we have x plus 9 and x plus 9. And then we have x minus 6, x minus 6. So we have 2 holes. We have a hole at x is 6. We'll go back and erase that just a little bit. And a hole at x is negative 9. Now with that there, if these cancel out, you're left with the 1 over x plus 9. So that means we have a vertical asymptote at x is negative 9. It's okay to write this. Technically, this only has a hole at 6 and a vertical asymptote at negative 9. However, the vertical asymptote is going to show a gap, so I'm okay with you writing this here for this particular class. When you get to the pre-calc and the college algebra, you will likely not be able to list that as a whole, but in keeping with geometry, sometimes it's better to have more information so that you can reflect upon it than not having enough information. All right, taking a look at the next one. Oh, don't know what I did there. Did something earlier. Okay. Finding the horizontal asymptotes. Okay, this one there are 3 different possibilities. Either you are going to have an asymptote of y equals 0. You'll have an asymptote of whatever your a and b is, or there will be no horizontal asymptote. Okay, the 3 different possibilities is with respect to degree of the function. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. If the numerator, the degree of the numerator, is less than the denominator, then you have y equals 0 as your horizontal asymptote. And then finally, the degree of the numerator equal to that of the denominator, y is equal to ab, where these would be the represent the leading coefficients of your equations. This is x to the first power, x to the first power, so degree 1, same degree. So then the horizontal asymptote of this particular equation is y equals, -2. I started to put there, but so -4/2, which is the same as -2. All right, just to add a few more examples because that is easy, but it's also brand new. Looking at the quick checks. All right, so this is degree 1 because there's a silent 1 there, and degree 1. So the denominators the degrees are same. So this is the same as -2/1. So y equals -2. We have degree 2. So we have 2/1. So your horizontal asymptote is +2. All right, last one that we're looking at is sketching the graph of the rational functions. So not easy if you do it all at one time, but you will need this in order to be successful because this lays the foundation work for stuff that you will do in the fall in pre-calc and in college algebra. Okay, we need to list a few things. First hour, third hour we did it. First hour, I'm adding this on there just to make it easier on you. So we've got actually 5 things we do. 1, 2, 3, 4, and then 5. Okay, the first thing we want to do is find the VA, the vertical asymptote. Then we want to find the horizontal asymptote. Then we want to find the y-intercept, the x-intercept, and then test areas. All right, the vertical asymptote is where your denominator equals 0. So that is going to be at x is 3 and x is -2. The horizontal asymptote, well, this is x plus 1. And then if I were to FOIL this out, this is the same as x plus 1 over x squared because we do x times x. Well, right there, I don't have to do anything else. This 2 is bigger than 1, so my degree is, the numerator is less than the denominator. So that means we have y equals 0 for the horizontal asymptote. Y-intercept is the same thing as when x equals 0. So putting in 0 here, you are going to have 0 plus 1 over 0 minus 3, -3, times 0 plus 2, which is 2, which gives you -1 over 6. X-intercept is where y equals 0. And in order for y to equal 0, this has to equal 0 because this won't have any effect on it. But if this is 0 over something, then you know y is 0. So x plus 1 equals 0, or x is -1. Okay, let's go ahead and sketch this. And we're almost done, guys. Sorry, these are not pretty. Okay, so graphing all these. The vertical asymptote is at 3. And it just goes through the 3 on the x-axis. -2. And then the horizontal asymptote is the y equals 0. So that's your x-axis. Y-intercept is at -1 over 6. The x-intercept is at -1. Because it's crossing, you know it's going to look, it's going to have to go on both sides. And these graphs love the horizontal, or love the asymptotes. They get really, really close to them. They like to hug them. They like to think of them as having a magnet in there. All right, so we've got the middle. Now we need to find out if it's going to be like this or like this. All right, so the way we do that is we take a value that is on this side of the vertical asymptote, -1, -2, -3. Let's pick -3. And we want to see if this is a positive or a negative. So since this is -3, we have -3 plus 1, which is a negative. -3 minus 3 is a negative. -3 plus 2 is a negative. Negative times a negative makes that positive. So a negative over a positive makes that negative. That means when it's -3, your graph is going to be down here because it's negative. And then we want to test something over here. So we have 1, 2, 3, 4, 5. So we put 5 in. 5 plus 1 is positive. 5 minus 3 is positive. 5 plus 2 is positive. So positive over positive is positive, obviously. So then there you go. So now you have your the sketch of your graph. And again, remember, I knew it was going to have to be really close to those asymptotes because they love their little asymptotes and they have to hug them. I will put some other links on there because I did find some things that might be beneficial to you. If you have any questions, please ask. You know where to find me.